everyone. So today I'm going to be talking to Carlos Morales, VP of AI at Ambiq. And we're going to be talking about addressing the diversity and constraint issues that Edge AI presents. Hi, Carlos. How are you?
I'm doing well. Thanks for having me on, Mike.
No problem. Great. So as we know, intelligence is going to be placed everywhere. It's no longer just going to have AI workloads being conducted at big centralized data center operations, but it's going to be at endpoints all over the place. Yeah. And obviously that's going to allow shorter latencies to be benefited from, etc., and more detailed analytics in real-time responsiveness and so forth. So first of all, Ambiq sort of is focused on 4 different areas. Maybe you could tell us about those first.
So we're really focused on anything that is battery constrained, like things that go at the far. So people talk about the edge AI, but they kind of fold things like laptops and smartphones into the edge. And we're talking about going beyond that. So things that sit on your wrist or sit in a factory, sit in a smart home, so on, that are running off a battery or running off something constrained, like harvesting energy and stuff like that. Those markets include things like wearables, so things that go in your ear, on your body-worn AI, like things that go in a smartwatch, but also health monitoring, remote patient monitoring, that's very important. Industrial applications, robotics. People don't know every joint in a robot, industrial robot, or the Anthropic robots that are making now, the joints have AI in them. If you think about, they're trying to follow the octopus model, where octopuses have octopi, octopuses have brains in every one of their limbs, right? They're kind of autonomous, and that's what robotics have to do. So when we talk about AI everywhere, we're not kidding, right?
Yeah.
Every little joint is going to have a little bit of AI in it.
So as you say, I mean, I didn't know it went to that level, but as you say, obviously one intelligence at a much more granular level and more ubiquitous, should we say. And as you mentioned there, so personal devices are important to you, and then sort of healthcare monitoring and industrial edge type things. So anomaly detection and so forth, and monitoring, sort of operational parameters to make sure everything's running well. And then I think you do quite a lot in sort of building automation and smart homes as well. Yeah.
Right. So, and when you think about the AI kind of side of that, right, the kinds of AI, what people in the AI industry call the AI tasks, don't fall into the neat categories that everybody, okay, this is an image classifier, this is a task classifier, and so they're pretty diverse. Yeah. So edge AI engineers, embedded AI engineers have to be thinking about what is the data that you're working on, and that data can be something like speech, like keyword spotting or something similar, simple and well understood like that. But it can also be some esoteric sensor that goes on your arm or goes in a robot that is measuring something that we hadn't thought about before. So it's a really interesting and challenging field in the sense that you can't hyper optimize for one kind of thing.
Yeah.
You can't do the ChatGPT thing where they do one thing. They do inference really well for, large language models, and they spent their days obsessing over key value stores and how to optimize RAM access. I wish I had that luxury of optimizing for one thing, but I don't. Right? It's like, oh, you want to measure crickets this week, right? Okay, let's figure out how to measure crickets using your cricket sensor.
I mean, so that's one key thing that we should maybe talk about in a bit more in depth is obviously the data center side of things, the centralized things. Mm-hmm. You're talking about big LLMs running on big GPU sort of processors and so forth. When you get to the edge, it's a lot more fragmented. The sort of, the possible use cases are, infinitesimal, I guess. And obviously you can't, the GPU guys can think about certain optimizations because they know that that's going to work for 90% of what they're doing. Whereas where you are, it could be a, completely different set of criteria that need to be solved by every different customer. So that must be a bit of a headache for you for starters, because every single thing is going to be slightly different and it's going to have different nuances to it. So first of all, I mean, how do you support that diversity of different potential models?
Well, so there is a positive aspect to it, which is it's tremendously exciting. Like, you think that you understand the AI, and then you talk to a customer that's doing some esoteric, crazy thing. You're like, no, hang on, you can, right? And then you start kind of meditating on how you would approach that problem. So you do try to categorize things into, you mentioned anomaly detection. That's a very broad case. It's really kind of trivial from an AI point of view, in the sense that the model itself will be trivial. Now, there are as many anomaly detectors as there are engines, right? Or so you have to customize each model for each deployment. And that's the hard part for anomaly detection. For the other classes of like esoteric things, what we realize is they all do multiply and accumulate. They all have to do the math at the end of the day. They all have to structure neural networks, and there's only maybe 30 or 40 operations that you have to do. So instead of doing what the cloud people do, which is here's a transformer attention-based model, and this is how we're going to optimize how we do inference on that, we have to optimize for all the different operations in every combination. And so that's what we at Ambiq call the picks and shovels, right? Instead of trying to create the end product or focus on one end product, you create the picks and shovels for our customers to go after every one of those little gold nuggets that are out there.
Sure.
And if you follow the California history at all, the people who made a lot of money in the gold rush were not the gold miners; they were the Levi's and the picks and shovel.
Because it would be the people who were supporting that. So, as you say that, you're much more about being an enabler for them to find their own way of addressing that issue.
Well, this is the only thing we can do. We can't anticipate every.
Absolutely.
Believe me, I thought I could. It's like, we want to monitor date palms. It's like, okay. Or there's some stuff that our customers are starting to announce that maybe when they announce, we can talk about them. But they are truly esoteric. You did not wake up this morning and think about AI for horses,
So they're pretty out there then. Okay, so that'll be interesting to find out more about. But as you say then, from your point of view, it's never dull in your place then, because there's always a different thing you're having to deal with. But as you say, it's much more then about making sure they got the picks and shovels. They can do the actual addressing their application, but they've got the sort of tools, the platforms to do that. Just a quick thing on that though, as you mentioned, there could be some simple sort of things that they have to deal with at the edge in terms of capturing data, but there's going to be a lot of multimodal type applications as well, where you might have to have some sort of sensor fusion. You might have different data sources all needing to be dealt with at once. So again, does that make your life more difficult?
From helping our customers understand and develop products, it can be more difficult. It's the diversity of models is also driven by the diversity of types of sensors. And just going back to the cloud analogy, you have text and you have images. Really, like you take the audio, you turn it into text. They have two kinds of data. Now, there's some diversity. The text can be tabular and all this other stuff. In the real world, the world that we live in, where we have to sense, there are so many different kinds of data. Even if you're just doing a vibration sensor, an IMU, inertial motion unit, monitoring unit, the sheer amount of data that can throw off, like one of the richest veins of data is a human body or any biological system, but really we care about humans more than anything. Just putting a vibration sensor on your wrist or on your body somewhere just throws off insane amounts of information. Now, we don't do anything with it. We go like, okay, you did this many steps. We do a lot of stuff with it. We detect fitness. Are you standing up enough? Are you running? Is your gait wrong? But we could do so much more. The density of data is insane. and multiply that by heart sensors, the PPG, the little lasers that go on your rings and on your hand and your wrists. Electrical data. Some of us were monitoring the Meta announcement quite closely. Everybody was excited about the glasses. Glasses are glasses. We have a lot of customers that have smart glasses. The thing that excited me was the wristband. That wristband is an ECG monitor basically on your wrist. And using AI, they can tell you where each joint in your finger is. That's called SEMG, surface electromyography.
Okay.
And I think that's one of the things in the future. The models are simple. The models will run even on our smallest our hardware devices, as long as you have enough power power budget to run them. And that's not a concern for Ambiq for the most part.
So that brings us on to another thing. So we covered the fact that there's a lot of fragmentation. There's potentially huge numbers of possible use cases that might need to be dealt with. But however you look at it, whatever those use cases are going to be, they've got to work at the edge, and that obviously brings constraints with it. So, I mean, that's in terms of size, in terms of cost, in terms of the memories reserves that it's got associated with it. But I guess most importantly of all, it's the power budget, as you just mentioned there. I mean, in quite a lot of the cases you said about, sort of things like the medical monitoring, that's going to need to be something that's always on. And, some of the industrial IoT stuff is going to be likewise going to have to be running 24/7. So, let's deal with the constraints a little bit. I mean, first of all, things like the cost and the memory reserves and the size of the chips themselves. I mean, those are, I guess, something that you're fairly comfortable with.
Well, so there are really three basic constraints, right? Compute. AI takes a lot of compute.
Yeah.
Memory. Models can be pretty bigger than we're used to in the embedded space, and power. You can solve the first two by throwing more power at it. You can put more chips, memory chips on your device, or make it a bigger device and just cram more memory on it. Or you could have higher frequencies. More frequency means higher power. If you don't solve the power thing, it's just you're producing a demo. Okay, you have this nice model running, and it runs for an hour. It's great for CES because it's wired to the wall. Everybody's, oh, look, it has AI. But once you start selling it, and we've seen these products where they fail in the market because going back to the glasses, I love these things, but I'm used to charging my watch every night. But sunglasses or reading glasses have to stay on your body 24 hours, right? Yeah. They have to be. You can't be. Oh, my sunglasses are out of battery, right?
Yeah.
It's not how the real world works. So power it's a problem for the cloud, right? Because power costs money, and it's really a big part of their total cost of ownership. Mm-hmm. But for embedded devices, it's existential. If you don't have good power, you don't have a product. You have a demo.
And like you say, consumers won't put up with something. It's like, oh, that's a nice fancy feature that it's got. It can do this. But it'll only run for a very short period of time, and that's not practical if you want to use it in a real world context, because you don't want to have to be plugging it in every couple of hours to get access to that. So I mean, equipment could potentially run very sophisticated models that that consumers are after, but at the same time, it might not be practical in terms of the battery charge that it can use up in doing that. So I think
we run into this all the time.
A big trade-off, and that's So how you're dealing with that as a company is to try and get the power budgets involved as small as possible, and you're using what you call sub-threshold technology, and that seems to be like a gray area outside what normal transistors operate in, and you're sort of pushing the boundaries there, basically. But by doing that, by not sort of using transistors in quite the same way, obviously that gives you massive improvements in power, but it makes those transistors more sensitive to other influences. So maybe you could tell us a bit about that.
Yeah, so that's Ambiq's entire claim to fame, right? The reason that we exist is because we figured out sub-threshold uh, computing. I've seen, I mean, anybody who's been in Silicon Valley long enough has seen many companies try to do sub-threshold, and it works in the lab as long as you have the exact right temperature and the perfect voltages and no variations. You made one chip, it works. You go to your bosses, look, it works.
Yeah.
When you try to multiply that by 200, 300 million parts, that's where the complications come in. Because, so what we're doing is, when you take your EE classes, they teach you what a transistor is, and they say, well, it's a gate. Treat it as a gate, right? If the gate logic, the input is above a certain threshold, call it 1 volt, that's on. If it's 0, it's off. And now you're using that to create binary logic. But it's not really a gate. It's an analog circuit, right? And so you can drop the volts from 1 volt to 0.8 volts, 0.6 volts, and it still kind of works, right? It's an analog signal, and that's what we figured out. How far down we can do that where it's still behaving like digital logic, and then what problems do you run into? The problems are voltage variation, for example. So our chips have very sophisticated voltage monitoring and adjustment. Most chips have a few voltage islands, 3, 4, 5. They keep those kind of static. We have about 50.
Okay.
And then we change those 50 voltage islands, all those separate little voltage islands, 50, 60 times a second, like a very high change rate. That's just one solution. That's your voltages. And so voltages vary based on temperature. One side of the chip gets a little hotter than the other. You have to change that side of the chip, right? Also, the batteries are voltage sensitive as well. So that's just one example. I'd like to use that one because it's easy to understand. But there's hundreds of little tricks that we do to make this sub-threshold work. The payoff, though, is we go from 1x, which is where everybody is, to 5x better, 10x better. Actually, the first time I measured, I'm coming up on 4 years at Ambiq. I joined the company. They gave me the spiel. Oh, this was super low voltage. It's like, sure, but let me check. Right?
Yeah.
Trust but verify. And they run my benchmarks, and I thought I'd dropped to 0. I mean, literally, it was I got the math wrong, because you're used to in silicon technology seeing a 10%, 20% improvement, not a 90%, not a 10x.
For sure.
And it was. I went and hugged my wife. I said I made the right choice. And we're taking full advantage of that. That's what my team's job is. You have all this free compute, basically, in terms of power. Use it.
But that's cool, because so then you're addressing how a transistor works, not as this ideal straight up and down switch type thing, but sort of able to deal with it as it is, as an analog switch, basically, and you can sort of mess around with that. But as you say, other people have tried to do stuff like that in the past, and they can do that in a lab because the operating conditions are perfect. They're all controlled. But obviously, then, as you said, the way you're compensating for that, you're monitoring everything many times per second to make sure that's not happening. But obviously, that's really important then, because if you've got a fitness band or something like that, that's going to be out in the field. The battery, the current coming from the battery is going to fluctuate by small amounts. The fact that it's being moved around and so forth, there's going to be potentially sort of issues about mechanical.
Right.
And obviously then temperature variations. It could be a hot sunny day, or it could be out in the cold, and any variations in that is going to have it. So that you've found a way to deal with that, get enough data to compensate for all that, and then basically say, okay, this allows us to push those edges further. Yeah,
that's just one of the things I use as an example. But there's also manufacturing variation. So on a wafer, you have a few thousand chips, right? Each one of those has different characteristics. So we have to trim those. Right? We, as part of our manufacturing process, we look at the performance of each one of those, and then have special techniques and some magic pixie dust where we kind of build in what that performance is. So every one of our chips you can consider to be customized, right, for whatever corner that thing was built in. There's many dozens of something like 60, 70 patents Plus, we have a lot of just techniques and there's a institutional knowledge, like insider,
Right. Okay.
and how we know that this stuff works to make it all work.
But like you say, some tricks of the trade, some sort of intellectual property, a bit of a mix of all that. And okay, so this is good. So you have managed to find a way to make that, sort of workable in a real world environment, which is great. As we said earlier, obviously the use cases are very fragmented, and you've got to give them picks and shovels to, the companies the picks and shovels to actually deal with that. But in terms of, I guess, how these companies are supported, because if you're talking on the data center side, they're big companies, they've got big engineering sort of teams and this, you get down to these smaller companies, they might be making, that might be a little startup making a health monitoring, piece of equipment or a fitness tracker or anything like that. They're going to have far fewer engineers. They may not have the expertise themselves as well. So I guess having the sort of support tools, the platforms that they can work with that can save them time is really important, and sort of so they can get things done quicker.
Yeah. So it's a funny thing. It's a pros and cons, right? The big companies have huge teams because what they're doing is very hard. From an AI point of view, the models that we produce are far simpler, right? They produce the 700 billion parameter models. We produce 300,000 parameter models. They're suited to what we do. So a data scientist doesn't need an NVIDIA superbox to train them. We train them on, like, I have a gaming PC below my desk, and when it's not playing Halo, it's training models, right? It's the same GPU for both. So producing the models is a lot simpler. Good, that's good. Now, having the knowledge to produce small models is not that widely available. And then when you try to intersect those data scientists who know how to do small models with firmware engineers who know how to write firmware, that intersect is almost zero, right? Our job is to make that bridge easier, so the data scientists can kind of live in the GPU/Python world. They don't have to worry about what that looks like in firmware. And the firmware engineers just take a model and say, okay, I'm just going to turn that into firmware and put it on. Normally that cycle takes a few days. Here's a TF-Lite file, which is from my Python, convert it to C, run it. Oh, it takes too long. It's too big. It doesn't have the accuracy. And then it goes back to the data scientist. He retrains, and she kind of goes around it and does it all again. That's days. For nothing, really, for just figuring out how long a model takes to run in firmware, right? So one of our biggest picks is what we call the NeuroSpots auto deploy. Automates that process. So you have one of our evaluation boards, you plug it into your laptop, you drop a model in, and 5 minutes later, maybe not even 5 minutes, sometimes 2 or 3 minutes later, it will give you full characterization of that model. How long it takes to run, how much power it uses per layer, our chips have these almost microscopic counters in them. It's wonderful, but they're super hard to decode, right? They're 70, 80 counters. So the tool will tell you, hey, these are your bottlenecks. Maybe focus on this layer, change the order of the inputs to that layer a little bit, and you get a 10% improvement. And so that iteration is now a lot faster. So that's just that's my favorite pick. But we have others, right? We have, when you run a model on the device, you use something called a runtime. On the embedded device, there's something that takes a model and executes it, does the inference. And the industry standard is fine. TensorFlow Lite for microcontrollers is basically what everybody uses, but it's not been optimized for a while. It's optimized for the benchmarks that are published. So we've taken it upon ourselves to optimize that further. We have an internal version of that, fully backward compatible. That's just up to 5 times faster. Same model, just 5 times faster on our device. And then we went a step further and we did something called AOT, so ahead of time, which is completely different from the TensorFlow approach, where they interpret the model in real time as you go through the model. And so we're getting much better memory. So remember, memory is one of the big constraints.
Sure.
Sometimes up to 60-70% smaller models doing the same thing, and as performant or more performant. So those are the kinds of tools that our team works on. We also produce models. If we see a model that's being used by a lot of our customers, like physio models, like heart detection, AFib detection, we'll make a model like that as a reference design.
Which is cool. And then that's available as a resource then for for customers to use as a starting point for developing their own thing. So that's cool. As you said, though, there's a couple of things just to pick up on there. Is one, just go back to as you were saying, data scientists on one side of the company, they're coming up with the model. They've got a more idealistic view of what the world's like, I guess. So they want to sort of, their objective is to get as high accuracy as they can and make the model as effective as possible. But then the guys who are the firmware engineers, then they're sort of having to try and fit it into the constraints we hit upon earlier, the power budget, the memory reserves, everything like that. So what happens is, from what you're saying, is they pretty much, the data scientists throw that over the wall at the firmware engineers. Firmware engineers have to try and work all that out, and then they go back and then say, well, there's not enough memory to do that. The battery's going to be too
that's the olden days.
all those sort of things. So there's an iterative cycle then, and that takes time. And obviously these companies, especially if they're smaller, they don't have that much time to deal with. They don't want to miss windows or opportunities. These are going to be competitive markets where they want to get ahead of the game quicker. So you can automate that and allow them to sort of get to their end goal a lot quicker. Is that pretty much?
Right. So the time to market is critical for these small companies, right? Actually, it's critical for everybody.
Yeah.
But especially if you're trying to get ahead of the competition, you need, a lot of our customers come to us with the model first. They consider the AI their crown jewels, and now they're finding ways to productize it, to capitalize on it. And so they use our tools to rapidly figure out what works and what doesn't on real hardware. And it can get very complicated. Like, the data scientist has one memory, RAM. That's it. Maybe a file, right?
Yeah.
In an embedded device, you have tightly coupled memory. You have SRAM. You have off-board SRAM. You have NVM. You have PSRAM. And the firmware guys are designing a system. They say, okay, listen, you can have this slice of PSRAM. Well, the data scientist isn't going to go figure out how performant is my model on PSRAM, right? Well, they can't. With a tool like AutoDeploy, you just dash PSRAM, and it will put there and tell you, okay, you're using a little bit more microjoules per inference, but it's a little bit faster, and so on. So those trade-offs are something that they can do very quickly as well. It's like figure out memory placement and all this other stuff. It really is trying to solve all the embedded mess that data scientists don't want to deal with. Just kind of abstract that away, focus on your model, keep your beautiful minds beautiful, and have a quick way of understanding what the impact of your decisions are.
So as you said, and that means that they get visibility basically of what it'll take. So as you said, the amount of energy per inference is going to be what if you've got a little bit more memory here, you can be able to do this, or if you can,
right.
So they've got a much better sort of idea of what's possible and where they might have to make compromises, or where they can get away with a little bit more, a little bit less or something. So I guess that's great, because as you say, they're not used to having to deal with that, and they haven't had the access to that data before. So that means that they can now sort of make better informed decisions, I guess. Yeah.
Yeah. And so maybe a concrete example helps, right?
Yeah.
There's two, you may have heard these terms before. There's convolutional networks.
Yeah.
There's a convolution. It's a very optimized kind of matrix operation. And then there's fully connected, the more traditional, like every neuron is multiplied by every neuron. So modern architectures still use both. They use convolutions, usually at the beginning, or maybe one fully connected, convolutions, and then fully connected at the end. So you still have to optimize for both. It turns out that fully connected is reading and writing a lot of RAM. It's just crazy, right? Because you're multiplying everything by everything. And caches don't help you there because you're walking through those matrices one by one. So very concretely, if you put that in a slow RAM, your entire model will go slower because it'll bottleneck on that.
Yeah.
So what we found is giving the data scientists that information can let them put that one layer in TCM in this very constrained, smaller memory that is much faster.
Yeah.
And everything else goes in SRAM or PSRAM. They get the benefits of both worlds, and their model is faster and more power efficient. But they wouldn't be able to do that easily if they didn't have these picks and shovels, right? It's hard to figure that first thing out. And if you have a little red flag that says, this layer doesn't belong here, it makes it a lot easier. And they don't have to write the firmware for that. They can just set a flag, and the tools will put it in the right RAM, which is, trust me, firmware engineers love that. They don't have to figure out, what is this model doing? How do I break it apart? It's just automatically, it's all done for you. So,
to sum up, it's clearly a question of having the hardware technology that you've managed to make these huge power savings, but it's also a question of having the tools and the sort of access to greater visibility of what's going on. That's going to help the engineers as well. So I guess that's a mixture of the two things. On one side, you want the chips to be able to to offer this sort of much more ultra power efficient sort of approach, but also have the supporting software platforms and so forth that customers can then sort of get further down the line a lot quicker. So that's cool. I mean, I think that's probably covers, from my point of view, that covers all the questions I had about it, and it certainly answered all of them really well. I mean, Ambiq's just sort of basically just done its IPO a few weeks ago. It seems like as a company, your share price is skyrocketed already. So you as you said earlier, you looks like you've made the right choice of joining them. So well, we look forward to seeing how the company progresses in the next couple of years. And it's been a real pleasure talking to you, Carlos.
Right, same here, Mike.
Thanks a lot. Cheers.